Hello. OTP 1 second. 890019. ठीक है ठीक है। हाँ हाँ ओके ओके। So good evening everyone. So today we will start our first tutorial class on this thermodynamic statistical mechanics from classical to so before starting our class, so let me just tell you what are the things that we are going to discuss in today's class. So first, initially, we will start. Just a second. Hello. Acha acha. Okay, 1 second. 826033. Okay. Okay. Sorry for the disturbance. So first we will discuss about what are the uh, importance of statistical mechanics. So as you all know, statistical mechanics is basically used to measure a average statistical property of a system. Okay, so like let's suppose a system is made of n number of molecules. Okay, now n is, let's suppose, a very high number like 10 to the power 23 order of number. Okay, so now in classically, like let's first talk about the molecules as a classical particles. Okay, so if you want to study the system classically, then what you have to do, you have 10 to the power 23 classical equation of motion, right? Like just like how we did in classical mechanics. Okay, so we have basically 10 to the power 20 the classical equations. Then you have to solve all those Newton's equation of motion in order to get the property of the system, right? Different types of property of the system. But for our, like, the type of computation that we have right now, that like simulating like equations up to the order of 10 to the power 23 is not possible. Actually physically is not possible. Like so in order to, so how can you do that? Okay, so how can you, just like so just ignoring that classical equation of motion, how can we like estimate the properties of a system, of a, like, a material? Okay, so in order to do that we need the statistical mechanics. Okay, so in statistical mechanics, what we do, instead of like solving the equation of motion of like individual each of the particle in a system, we basically do a statistical average. Okay, what is statistical average property of the system? So in order to do this statistical average, we basically need this tool. this statistical mechanics basically act as a tool in order to estimate this statistical average properties. Okay, so that is basically briefly I give you a kind of a importance why we need statistical mechanics. Okay, so basically to make our life simpler. Okay, so so let's so before going to the problem, okay, I mean solving the problem, let's just first discuss about some of the topics, basic topics that we need actually, like basic concepts that we need. Okay, so in general in statistical mechanics we like in beginner level we take a system which consists 10 molecules, right? Now let's suppose this is a fixed energy system. So the total energy of the system is fixed. Okay, so that means that each of the each molecule has some definite energy, right? So each of the molecule has some definite energy level. So because of that, the total energy of the system is fixed. Okay. Now, what we have to do, like, let's suppose these are the some energy states. 1, 2, 3, 4. Let's suppose this state has energy E0, this state has energy E1, E2, E3. Now, if n is the total number of molecule, then out of this n molecule, let's suppose n1 number of molecule is in state E0, n2 number of molecule is state E1, n3 number of molecules is state E2. So like this, the whole n number of molecules are distributed into the system. Okay. So our main goal would be what are the distribution, for today's topic we want to evaluate how like the this how like this n1 number of particles out of this n total n number of particles, how this n1 number of particles is distributed in the level E0, similarly how n2 number of particles is distributed in E1. So that distribution you want to find out. Okay, so basically you want to find out the population of the molecules in each of the state. Okay. So and we like later stage we will like find out that this thing also depends on a temperature. So this whole thing we have to find out at a constant temperature T. Okay. So and other thing is that this states for simplicity you are considering that these molecules, like the molecules should be independent. Okay. And also you are considering that the molecules are not interacting. Okay. These are the like basic assumptions that we consider. Okay. So So and so I guess like in previous prior to this course, like I guess you already know about this theory of this, or this principle also need in order to develop some of the concept. This theory is called principle of equal equal priori probabilities. So what this principle tells us, this is one of the fundamental principle of classical statistical mechanics. So this principle basically tells us, so so all possibilities for the distribution of energy are equally probable. So the in a distribution, all the possible all the possibilities of a distribution of the energy are all equally probable. Okay, this is the principle called principle of equal a priori probability. I guess this has been taught in previous to this course. Okay, so so these are some basic things about statistical mechanics. Why we need to read statistical mechanics? What are the things that we want to basically interpret using statistical mechanics? So now all this in our hand. Now we will discuss, like, in order to solve problems, we basically need some of the things, like some of the concepts that you already need, like we need in order to solve like this numerical problem. So the first thing is what? Let me write it. Weight of the configuration. Okay. So uh, let's suppose I have n numbers of molecules. Okay. Or suppose anything, n number of balls maybe. Okay. N numbers of balls. Okay. Identical balls. Okay. So all the balls are basically identical. So let's suppose, just like the energy state, let's suppose there are some boxes are there, like let's suppose this is box 1, this is box 2, this is box 3, so like this. Now out of this n number of identical balls, let's suppose I put n0 numbers of ball in the box 1. So let's suppose there are n0 number of balls are there, n1 number of balls, let's tell it b0, then it will be conventional. B0, box 1 B0, box 2 B1, box 3 B2. Okay. So n0 number of molecules in box 0, n1 number of molecules in box 1, n2 number of molecules box 3, similarly up to box n, n numbers of molecules. Okay. So all this 0, n1, Nn is equal to n. So this is also a constant into the system. So total number of the molecules is fixed. We are considering in a system where the total number of these balls are fixed. The balls are identical. Now we distribute this ball into this different box, like box 0 has n0 number of balls, box 1 has n1 number of balls, box 2 has n2, box n has nn number of balls. So now what are the different ways? Okay, like what are the different configuration, you can say, the way, like the configurations by which we can basically distribute these balls n0, n1, n2, number of balls into these boxes, into the boxes. Okay, so this is basically known as the weight of the configuration. Okay, so let's term it as W. Okay, so W is basically called the weight of the configuration. This basically means a general configuration where this n0, n1, n2, nn number of different ways by which the n total numbers of ball are can be distributed in the boxes. Okay, so this is called the W weight of the configuration. For our case, since we are like distributing the balls in the box, it can be in numbers of molecule in the energy state, like depending upon your system. Okay, the weight of configuration, like the definition of the weight of configuration will be different, definitely. Okay, so for this case, the mathematical, like the expression of the this weight of configuration, this W would be, so the mathematical expression of W is given by W equal to n factorial n0 factorial n1 factorial n2 factorial . Okay, so this is basically the expression of the weight of configuration. Okay, so that means, okay, so factorial means like 6 factorial means, I guess you all know, is 6 into 5 into 4 into 3 into 2 into 1. So factorial of all x is like x into x minus 1 into x minus 2 into, this is the meaning of the factorial. Okay, okay, so the main thing that I want to say though, so if you want to like distribute identical particles in different like boxes or different configuration, like so the number of ways you can do that is given by this formula. Okay, this is the formula. This is the formula. This is called the weight of the configuration. Okay. Okay, so let me do a simple example. Okay. This is my guess. So let's suppose that this total number of ball is n equal to 20. Okay, so now let's suppose n equal to 30. Okay, so let's suppose the number of ways you can arrange this ball is like 1 0 3 5 10 1 5 5. Okay, if you so these are the like in different boxes you put, like in box 1 you put the 1 ball, in box 2 you put 0 ball, in box 3 you put 3 ball, in box 4 you put 5 balls. So like this you have distributed the balls inside the box. Okay, so now Now if you calculate, so the total number of ways, W would be, how can you calculate W? It would be n factorial n1 n0 factorial n1 factorial n2 factorial, like that. So in this case it would be 30 factorial 1 factorial 0 factorial 3 factorial 5 factorial 10 factorial 1 factorial 5 factorial. Now if you calculate this in calculator, this basically gives you a value like in the order of 10 to the power 9. Okay, so this should be the number of ways that you can number of ways you can uh, distribute this particular configuration. Okay, this particular configuration inside how many boxes are there? So 1 2 3 4 5 6 7 8, so 8 boxes are there. So this configuration can be done by in 10 to the power 9 different types of ways in 8 boxes. Okay, so this is how you can calculate the weight of configuration. Okay, so now let's do a problem. Okay, so I hope you understand. So let's do a problem first. Okay, so problem number 1. Four indistinguishable coins are tossed a large number of times. Write down the different microstates which may be observed and the macro states they would form. Give the probability of the most probable microstate. Okay. So basically you have 4 distinguishable coin. Okay, so when that means each coins are different from each other. It's different, like in case of if it's an identical coin, I mean so identical coin means indistinguishable. So in case of indistinguishable coin, so the problem would be different. Okay, but for this case, these are 4 distinguishable coins. Okay, so that means so when a coin you can toss, it can be either head or tail. Okay, right? So the possibility of getting head would be half, the possibility of getting tail would be half, right? So in this way 4 distinguishable coins are tossed at a large number. So that means they ensure that there is no like weightage, which there is no weightage associated with a certain configuration, right? That's why they have mentioned that this experiment has done at a large number, and they have like asked us to calculate like different microstate. Okay, different microstate under a macrostate. Okay, so like macrostate like different configuration, either it would be a head head or tail tail, or it would be a tail head head head. So these are called the microstate of the system. Okay, sorry, the macrostate of the system. So under this macrostate, how many ways this head tail 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 is can happen? So this basically gives you the microstate and comes under that macrostate. Okay, so okay. So let's there are 4 points. So let's just write the problem. So like in the problem you have to calculate like the probability of each of the macrostate and what are the most probable microstate. Okay. So sorry, what are the most probable macrostates? Should be macrostate. Let's see. Macrostate. Because microstate decides the probability of a macrostate, right? So right now, so let's that 4 points, right? So this is so point 1, point 2, point 3, point 4. So let's call point 1 as A, point B as B, point C as C, point 3 as C, point 4 as D. Okay. So let's suppose so let's build a chart. So building a chart would be helpful to to analyze the different possibilities. Okay, so let's write the chart. So so here write the macrostates, and under each macrostate there will be microstates, points having head, microstates, points having tail, number of microstates, and probability. That's the main important thing. Okay. So it's okay. So let's take first case where let's suppose all of the points are head. Okay, so N1 means the number of points which are having heads, and N2 is the number of points which are having tails. So let's first take the consideration that a configuration where all the points are having head. Okay, so 4 points are having head and 0 points are having tail. So what are the different ways that we can achieve this configuration? That would be all the ABCD are having head, right? A, B, C, D, all are having head, and no points are having tail. This is the only ways to have this configuration, right? So the number of under this macro state, the number of microstates should be 1, right? Probabilities will calculate later. Okay. So under this macro state, the number of microstates should be 1, right? Now, so this is one problem. So this is one macro state. Now next, consider another macro state where let's suppose out of these 4 points, let's suppose 3 coins are having head and 1 coin is having tail. Okay. So out of this ABCD, That means either A, B, C can have the head, then D will be having the tail, or B, C, D can be having head, then A would be having the tail, then C, D, A can have the head, then in that case B will have the tail, and at last D, A, B can have the head. And in that case, um, C would be having tail, right? So for this microstate, you can see for this microstate, let me just distinguish it. Uh, so for this microstate can be achieved these four different ways, right? Like this, all these points are like in distinguishable, right? So, and we have marked each of the coin like A, B, C, D like this, right? So this is a possible combination of like having three heads, and this is like three coins are having head, and this is the combination like the rest of the coins is having tail, right? So so the number of total microstate would be in that case would be four, right? Number of microstate would be the four, and this is the basically the description of all the four microstates. So then there is also another microstate, right? Where let's suppose in one like number of coins that are having head, that number is, let's suppose 2, and number of coins that are having tail, that number is 2. Okay, so now for this particular macro state, the number of microstate like the coins are having head would be A, B, then that case C, D would be the coin that are having tail. Number of ways A, C having head, then in that case B, D would have tail. A, D has head, then B, C would have tail. If B, C has head, then A, D would have tail. If B, D has head, then A, C would have tail. If C, D has head, then A, B would have tails. Okay. So as you can see, so for this kind of this macro state where two coins can have tail and two coins have tail, these are the all possible configuration. Okay, you can also check it later, like this is like pure using intuitive thought I'm doing it. So these are the like possible configuration of having this particular microstate. Now the number of total ways would be 1, 2, 3, 4, 5, 6, right? So 6 different ways, right? So far the highest number of microstates we are getting here, right? 6. Next would be the opposite of the second one, where the number of heads is 1 and number of tails is 3. Okay. So this would be the opposite of the second macrostate, right? So here, if A is having the tail, then B, C, D would having the A is having the head, and B, C, D would be having the tail. If B is having the head, then A, C, D will have the tail. If C is having the head, A, B, D would having the tail. If D is having the head, then A, B, C would have the tail, right? So these are the 4 different combinations, right? This would be definitely be similar to the second macrostate where like number of heads is 3, number of tails is 1. Here the thing is like opposite, number of head is 1, number of tails 3. So here also, okay, 1, 2, 3, 4, 4 possible combination is there. So this is the 4, and lastly is the like the opposite, like the first combination, right? Where number of coins that is having head is 0 and number of points that is have tail is 4, right? This is only as you have guessed, only like one possible configuration is only can be happen in this particular macro state, and that would be uh, nothing is having head and all the points are having tail, right? So this is like 1, right? But this, as you can see, is just the opposite of what we are having like first macro state. Okay, so these are the all the possible macro states that comes under, like when you like tossed up 4 different points and you measure the probabilities like at a very large number of experiments during the same day experiments. Okay, these are the possible macro states you can get. Okay, and also like under each macro state we have like done the calculation of like each micro state that comes under the macro state, and so far what we get this this second case where number of heads are 2 and number of tails are 2. That particular macro state is having the highest configuration, this is 6, right? So if you calculate the probabilities, so so total number of microstate is how much? 1 plus 4, 5. So 6 plus 4, 10. 10 plus 4, 14. 1, 15 and 16. So total number of microstate is 16. Okay. So here total microstates is 16 and total macrostates is how much? 1, 2, 3, 4, 5, right? 5 macrostate is there and microstate is 16. Now calculating the probability is the easiest thing. Just divide this number of microstate with the total number of microstates, right? 1 by 16 in this case. This case it would be 4 by 16. This case it would be 6 by 16. This case it would be 4 by 16. This case it would be 1 by 16. Now if you just like, so if you add like all of these probabilities, you will get definitely 1. That's for sure, right? So so everything is consistent with each other. So now, so as you have guessed, intuitively guessed earlier, right? So the most possible, like the most probable most probable macrostates will be this state, right? With having head equal to 2 and n equal to 2, tail equal to 2. Okay, so so let me write it. So the most probable state is n1 equal to 2, head equal to 2 and n2 equal to 2. Okay, this is the most probable, and the probabilities 6 by 16. Okay, 6 by 16. Okay. so this is the way. So let me just recap what we have done. So the question is like we have 4 distinguishable points are tossed at a large number. Then like you have to calculate a defined microstates under defined macrostate, and from that you have to calculate the what is the most probable macrostate. So for that we like need some like basic statistical intuition. So for that we have first write what are the possible ways like the coins can be arranged, right, after each tossed. So these possible ways are basically nothing but gives you the macro states. Like either it can be all points can be heads, or 3 can be heads, 1 can be tail, or 2 can be head, 2 can be tail, like that, or like that. So or it can be 4 of them can be tail. So these are the like possible configuration which you can tell as a macro state, and under each macro state you are calculating these micro states. Okay, so that basically gives you the possible configuration this map in like the way these macro states can be arranged. So from there we have calculated the probabilities. Okay, like for n4, n0, n3, n1, N12, N22, N11, N23, so like that. So total number of macrostate we got 5 and total number of microstate we get 16. And the most probable macrostate that we got is this one, where the states are actually widely distributed in this case, but the number of heads is 2 and number of tails is 2. So so this state is like the most probable states. Okay, so 6 by 16. Okay, this is the way you should calculate this problem, this type of problem. Okay, so now so now so this is the problem of points. Now we will shift. Now we will do a similar type of problem, but now this case we will shift towards a more like science-based problem, or you can say a more material-based problem. So, but the concept that we will use for the next problem would be the same, just like we have did like in the previous problem. So let me write the problem. Okay, first. Suppose we know three particles will spin half get into homogeneous magnetic field B at temperature T. Okay, so now we have to find out A, show all possible microstates and corresponding probabilities the average value of spin C if mu b is magnetic moment which can be figure as maximum energy. And what is corresponding probability? So So let me, before solving the problem, let me just tell you a bit about spin-up particles. So what is the spin-up particles? That means the particles basically has magnetic moment. Okay. This means that when you keep the particle in external magnetic field, okay, so either it can have a spin half configuration plus half configuration, or it can be in a minus half configuration. Okay, so just like the coins, like, so it can either have a head or it can have a tail. So similar way here, when you, like, if this is a magnetic field B, so there are three particles. Okay, so three particles are there. So this kind of like this magnetic particles, we denote its spin by using an arrow. Okay, so this is called spin up, this is called spin down. Okay, so particle can have this configuration or can have this configuration. Okay, so in so there are three particles are there, which basically placed into this these are the spin-up particles. Okay, so when these particles are like kept into the homogeneous magnetic field at a temperature T, either like all the three particles can have spin up, or some of them can have spin down, or some of them can have spin up, or all of them can have spin down. So we have to calculate what are the different possibilities. Okay, and in this case the main thing is three particles are identical. Okay, like in the previous case, like what we have done, like, so this particles are distinguishable. In this case, like, the particles are identical. So okay, so so when the particles are, when it's spin half, then it's basically magnetic moment is written as h cut by 2. H cut is nothing but Planck's constant, as you know. When it's spin down, this magnetic moment is h cut minus 2. Okay, because sorry, this is spin value. Sorry, this is spin value, s value. Okay. This is needed because in this problem you have to like, this problem asks you to find out the average value of spin. So when the particle is pointing in upward state, that means the particle spin is h cut by 2. When the particle is pointing in down state, then its spin value would be minus h cut by 2. So now let's also build a table like the way we have done previously. Okay. So so configuration microstates and probability. Okay, so let's in the chart. Okay, so now so as you have all guessed, so what is the first configuration, or the macro states, whatever nomenclature you can use? So that would be all are in the up state, right? Basically all the particles, all of the three particles basically pointing like in the spin half configuration, basically spin up configuration, basically. So in that case, the there is only one possible microstate, that is one, three particles are basically pointing upward. So three are the spin up states. We'll calculate the probabilities later on. Okay, after getting all of the microstates, where basically we will calculate the probabilities. Okay, next configuration would be 2 are up and 1 is down. So in this case, what are the microstates? So microstate would be 2 up means this one is up, this one is down. In this case, this one is up, this one is down, this one is up. In this case, this one is down, this one is up, this one is up. So up, up, down, down, up, down, down, up, up. Right? 2 are up, 1 is down. So all these triggers, 2 are up, 1 is down. Okay. So this case 1. This case it's 3 microstates are there. Second is the opposite of the second one, that is 1 up and 2 down, right? So 1 up and 2 down. So for that, the number of configuration would be down, down, up, up, down, 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 up, down. Like basically the transpose of the inverse of the microstate of the first thing. Okay, so 2 are down, 1 is up, 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 down, 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 up, down. Okay, so these are also 3 configuration. And the last one, like the opposite of the first one, so that is all 3 are down, right? So for that, this would be down, down, down. This will be one case. Okay, so you get it, right? So 3 particles, any of can have up or down, just like the problem we have done with the probabilities. Like in that case, the particles are simply replaced by the points, which can have either head or tail. So the possibilities, right? So the number of total microstate is like 3 plus 3, 6, 1 and 1, so 2. So total number of microstate is 2. Total number of microstates is 8, right? 3 plus 3, 6, 7, 8. Okay. Total number of microstate is 8. So total number of microstates is if 8. So that in that case, the first configuration has a probability of 1 by 8. The second configuration has a probability of 3 by 8. The third one has the possibilities of 3 by 8, and the last one is having the possibility of 1 by 8, right? So these are the 4 possibilities. So now the first thing in the problem, that is we have already calculated. So all the possible microstate, its corresponding probabilities, that we have already shown. Next thing is we have to calculate the average spin, right? So average spin. So spin, average spin, right? So okay. So let's, what I can do here, we can add another, maybe another column here. Was probabilities. In this, then you can add another column of spins, because that is also required, right? Let's add another column of having title spin. Okay, so now in this case, I have to tell you, right, like if the particle have spin of configuration, then its spin value would be h cut by 2. If it having a spin down configuration, then its spin value would be minus h cut by 2, right? So now when all the particles are in spin up state, its spin value would be 3 h cut by 2, right? H cut by 2, h cut by 2, like this having h cut by 2, this having h cut by 2, this having h cut by 2. So total spin would be 3 h cut by 2, right? In this configuration, 2 having upward, 1 having downward, that means h cut by 2 plus h cut by 2 minus h cut by 2. this because of one spin is down here. So that gives you h cut by 2 plus h cut by 2. In this case, minus h cut by 2 minus h cut by 2 plus h cut by 2. So that gives you minus h cut by 2. Right. In this case, it would be 3 spins are downward. That means it gives you minus 3 h cut by 2. Minus 3 h cut by 2. Right. So these are the spins, and these are the spins, and these are its corresponding all the possibilities of so in order to calculate the average value, you know the formula of the average, right? The average of a spin would be the number summation over the number of spins and its corresponding probability, right? Into its corresponding probability, right? This gives you the average spin. So first case, the spin is 3h cut by 2, right? And its corresponding probability is what? 1 by 8. In the first case, the spin is 3h cut by 2 and its corresponding probability is 1 by 8, right? So 3h cut by 2 into 1 by 8 plus, in the second case, the spin is h cut by 2 and its corresponding probability is 3 by 8, right? So in that case, it would be h cut by 2 into 3 by 8, right? 3 by 8. In the third case, the spin is minus h cut by 2 and its corresponding probability is 3 by 8, right? So it would be minus h cut by 2 and its probability would be 3 by 8. In the fourth case, the spins are basically 3h cut by 2 minus 3h cut by 2 total spin value, and its corresponding probability is 1 by 8, right? So it would be 1 by 8 into minus 3 h cut by 2. Now if you calculate all of this basically gives you 0, okay, because this gives you 3h cut by 16, this gives you 3h, this also gives you 3h cut by 16, this also gives you minus 3h cut by 16, this also gives you minus 3h cut by 16. So total value will be 0. Okay. Okay. So now last problem. So in the last question, they have asked to calculate what is which configuration has the maximum energy. Okay. So what happens in this case, when the particles are in the spin-off state, the energy is basically minus mu b into b. Okay, and when the particle is in down state, this energy would be plus mu b into b. Okay, mu b is just a factor. Okay, and b is the magnetic field. Okay, so when it's half plus half and this is minus. Okay, so so in the case 1, the energy was like 3 particles and the so in the first case, of all the particles, 3 particles are the in the spin-off state. In that case, the total energy would be minus 3 mu b into b. In the second case, when two particles in spin up and one particle in spin down state, in that case total energy would be two particles are having so upward and one particle is downward, so that means the total energy would be minus mu b b. In the third configuration, two are down and one is up, so in that case the total energy would be 2 mu b b minus 1 mu b b, so it would gives you plus mu b b. And in the fourth configuration, the total energy would be all of the three particles are basically pointing downward, spin down particles. So in that case, the total energy would be plus 3 mu b b. Okay, so that means that in this fourth configuration, that means in this case, when all the three particles are basically having spin down state, that case would be having the highest total energy. Okay, so let me write the answer. So the magnetic moment of configuration in which all three are down in this configuration, just to be specified, have magnetic moment minus 3, plus 3, not magnetic, energy, energy 3 mu naught b. Okay, so this is the most energy configuration, and the probability of this configuration would be 1/8. Okay, so right, you get it right. So the thing is, you have like some like spin up particles. So you basically put it in a magnetic field, homogeneous magnet at particular temperature T. So either the particle can have spin up or spin down state. So spin up state, the spin value is h cut by 2, and spin down is minus h cut by 2. So all the possible configuration you can write for three particles are there. So either 3 of them in up state, 2 of them down, 1 can be up. 2 can be up, 1 can be down, or either 2 can be down, 1 can be up, or all three of them can be down. So these are the configurations, and for each of the configuration, you basically calculate the probabilities and its corresponding spin values. Okay. So after doing all of that, you get the total number of microstates, which is 8. That basically, but by doing that, you can get the probabilities, you can get the spin. So from that, you have to first calculate what is the average value of spin. That is the spin multiplied with its corresponding probabilities. That basically gives you the average spin value that we get here. So the average spin value is basically this, which basically gives you the 0. Actually, the average spin value got here 0. Anyway. Next we have been asked to calculate what is the maximum energy that you can get in the system. So the maximum energy, if the particle is spin up state, its energy will be actually minus mu b into b. If it's spin down state, its energy will be mu b plus mu b into b. So for each of the configuration, I've calculated the total energy. First case is minus 3 mu b b. In second case, minus mu b b. In the third case, plus mu b b. In the fourth case, it's plus 3 into mu b b. So that means that the fourth case where all the spin states are down is having actually the highest energy, and the probability associated with this highest energy configuration is 1/8. Okay. So this is it. So this is how like we can calculate like some of the problems that is associated like with configuration, like when like a particular macro state is given, like how many ways that particular configuration can happen, you can calculate in the system uh, by doing like simple some probabilities concepts, okay, for distinguishable as well as indistinguishable particles. So now we are bit shifting about like the things that we are intending to calculate, that we have talked in initially, like how the basically the particles are distributing like in different energy levels, right? So before like uh, in a way you can say the concept about the partition function of the system, okay, basically that this thing basically means that actually with the distribution of the particles. So for that, let's just first build some basic mathematics behind the concept of this partition function. So, so let me first write the, so in previously, we know about this configuration and weights, right? So, so W was, the weight was like if there is n total number of particles and number of waves like n0, n1, n2, number of ways, if you can arrange the particles, the number of weights can be uh, as we have discussed earlier, it can be n factorial by n0 factorial, n1 factorial, n n2 factorial, and so on, right? So these are the weights. So as you can see, this numbers can be become tremendously huge. Okay, so it's better to do a logarithmic to like deal with the logarithmic term, logarithmic version of this weights. Okay, so we take the lesser log in the both side, because uh, you can see like in previous like one of the sample problems, you can see the number of like the arrangements went up to the 10 to the power 9 order. Okay, so it's very difficult to like handle a such huge magnitude of number. So it's better way to take log of this number. Okay, so for that reason we are taking log in both the sides, so ln this side and ln in right side also. So n factorial, n0 factorial, n1 factorial, n2 factorial, blah, blah, blah. So I take log in the both the sides. Now, uh, now we can write it this ln w into ln n factorial, ln n factorial minus ln n0 factorial plus, sorry, let me just write it down. Ln n0 factorial into n1 factorial and n2 factorial, like this. As you can show in log, we can inside log we can write this divide as subtraction, right? This is the basic logarithmic operation, basic property of logarithmic operation, right? Now ln n factorial is there. Now you can write this as, now similarly in multi when like in logarithmic operation you can write this multiply as addition, right? So ln n0 factorial plus ln n1 factorial plus ln n2 factorial, so like this you can write. So now we, now here we will use an approximation what is known as a Stirling approximation. Okay. So by using the Stirling approximation, we can write this ln factorial. If 8 is a very large number, Okay, then we can use this Stirling approximation by writing ln into n factorial as n into ln n. Similarly, here you can write it as n0 ln n0 plus n1 ln n1 plus n2 ln n2 plus dot 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 dot. Okay. This is like a very like acceptable approximation that we are taking here. So this is, let me write it. This is using Stirling approximation. Okay. So now we can write this ln w as n into ln n minus I summation. Let me write this whole thing as a summation ln ni ln ni. So I basically runs from 0 to whatever number. Okay. So now so now from here, if you want to find out uh, what would be the, now our primary goal is like in the previous problems also we are like very keen to find out that what is the most probable distribution, right? So in the actual problem also, like when you deal with the physical problem also, like the thing that you would be wanted to calculate, like you will be tempted to calculate will be the most probable distribution, like the most probable configuration, right? So so how can you do that in this case? Okay, so in this case you can do it by using, so let's suppose a function f(x), a function is there. How can you find out for which x value the function can be will attain its highest value? Okay, so in order to do that we take the derivative of the function with respect to x, right? And find out at which x point this derivative will become 0, right? That x point is basically gives you the extremum point. Okay, and further we do the double derivative, and from there we will like confirm whether for this point will be maximum. The similar way here also we have to take, in order to find out the maximum of this maximum like the maximum acceptable configuration, we have to do the derivative of this first order derivatives of this weightage w. Okay, so that can be written as I delta ln w into del n I into g n I. Okay, so this is the function because we are doing the total derivative, right? So total derivative, if we are doing total derivative, then we have to consider what is the implicitly and explicitly what are the dependent variable in the function. In this case, the ni, the small ni, is basically the variable inside this function w. So that's why we're doing this partial derivative, and we are like writing it like this kind of a chain rule. Using the chain rule, we are writing the total derivative as like in terms of this partial derivative. Okay. So now, okay. And next thing is, I forgot to mention. There is some constraint into the system is there, right? So the first constraint is total, because this when you like when you find the maximum of the function, it is always important to also consider the constant into the system, because in that weightage function the constraint is not there, right? So we have to write a constraint of this particular configuration. The first constraint is the total energy of the system is constant. Okay. So how mathematically can you write it? You can write it like Ni Ei is E. That is the total energy. That is fixed. Fixed. So if like E0, E1, E2. Okay, so if N0 is having E0, N1 have E1, N2 have E2. So the total number of energy will be N0 into E0, N1 into E1, N2 into E2. So like that, the total number of energy will be E. And second constant is total number of particles will fixed. Okay, so this is another constant. So Ni would be N, right? So these are the two constraints. Okay, so now in differential form, you have to write this constant in differential form. So in differential form, this constraints can be written as Ei into dni equal to 0. This is the first constraint, and the second constant can be write as dni equal to 0. Okay. So now, so what we got? We got this. So we got this equation. We got this function that you have to find this maximum value, and these are the constants that are bounded with the function. Okay, so now what we can do, we have to write, so by considering the constraints into the function, we have to write it, right? So for that, what we can do, this is the differential form of the function or the weightage function. This is this. Now inside it, we have to implement the constant, right? So the first constant is plus dni. The second constant is plus, sorry, this summation is there, summation of I dni. The second constant is summation of I ei dni. Okay. Now, so these are the two constraints. Okay, so now in front of the constants, we have to multiply some factors. Okay, so these are basically called multipliers. Okay, so this is, in this case this will be alpha, in this case it will be minus beta. Okay, so these are basically called, this method is actually known as Lagrange undetermined multiplier. Okay. This method is called, this alpha beta is basically the multipliers. Okay, so these values of the alpha beta also have to calculate, that we will do later on. First let us write the equations. Okay, so now the whole, let me write the whole thing. So so if we write it in a proper way, it would be, looks like this: d ln w is summation over delta ln w delta ni plus alpha minus beta ei. You can take dn as a common. Okay, and this whole quantity we have to equate it with 0, right? So this is our main goal. Okay, so either you can write it also like this, also like this, delta w delta ni plus, as dni can never be equal to 0, so we can write it like this, alpha minus beta 0 equal to 0. So now okay. Okay, so this is the form that we get after considering all the constraints and everything into the equation. These are the final form that we get. So now we have to extremize it. Okay. So now for doing that, first what we have to calculate, we have to first calculate this quantity. Okay, this thing, delta lnw plus delta ni. So how can you do that? So for that, as we know, what is the expression of lnw? So lnw is nothing but n into ln n minus factor summation over ni ln ni n. So now we have to do the derivative. Okay, so delta lnw into delta ni. So the first would be, let's do the first case. Okay, delta n into ln n into delta ni. So this gives you, so first n would be outside, then delta ni would be outside, delta ln n by delta ni plus ln n is outside now, so delta n into delta ni. This gives you n into delta n by delta ni plus ln n into delta n into delta ni. This gives you 1 by ln n into delta n into delta ni. This is the first term, and the second term would be delta ni summation over I ni. This gives you summation over I delta del ni ln ni. This gives you summation over ni, or you can write it like okay, so here if I am using I, so I can write it as j. Okay, j, because this is outside the summation, right? So I can write it as j. Okay, that's fine. So, or I can write this one as ni delta ni, and this one as j. This one as j. Summation is over j now. Okay, like just to be distinguish the two summations. Okay, so delta and j. Okay, so now ni and j delta ni by delta nj by delta ni plus ln nj, this is nj, delta nj delta ni delta nj delta ni, sorry, nj delta ni. So this gives you basically summation over j 1 by plus ln nj into delta nj delta ni. Okay, this, so NiNT is basically, so this to this 2 will basically get cancelled, so this gives you 1 plus NG. Okay, or okay, so now if you substitute this to here, this gives you let's try to write it. This is a minus, so minus. Okay. So now the whole equation would be delta ln W plus delta Ni plus alpha minus beta Ei equal to 0. This is the equation now. 1 plus ln N minus 1 plus ln Ni plus alpha minus beta Ei will equal to 0. Now here, if you do ln Ni by n plus alpha minus beta Ei equal to 0. Now from here and write ln Ni by n equal to there's a minus n there. Okay. So alpha minus beta Ei. So now this gives you Ni by n equal to the power alpha minus beta Ei. Okay. So this is the most probable configuration. Okay. This configuration, like more precisely Ni, the configuration, the ith state is this. Okay, the most probable configuration. Okay, now here you can easily calculate this value of what is this called, value of this alpha and beta. It's not a difficult thing. Okay, so say alpha and beta basically related. Okay, so if you want to evaluate alpha and beta, it's not that difficult. So alpha beta evaluation is would be like this. So summation over I Ni over I n, because like in this equation I'm summation over the I n into the power alpha into the power beta Eg. So total number of particles is n. This is gives you n into e to the power alpha I to the power here. So e to the power alpha is nothing but 1 by summation over I e to the power minus beta n, right? So you can just substitute this e to the power alpha in this expression, and that basically gives you Ni by n equal to e to the power beta Ei by j e to the power beta Ej. This is the most possible configuration. Okay, and this distribution is known as the Boltzmann distribution. Boltzmann distribution. So in the later stage, you can see this beta would be nothing by 1 by AB3. Okay. So in the way that that this thing can be like proved in later stage of the course. You can see beta is nothing but 1 by kbt. So if you plug this into this Boltzmann distribution, then you can get how this distribution is dependent on the temperature of the system. That's why in every problem you can see the temperature of the problem is specified, because if you change the temperature, the distribution will be also get changed. Okay, so the temperature is always very important in this kind of system. So anyway, so that means that if you have like this kind of states, E1, E2, E3, E4. So the number of way like N0 or N2, N1 or N2, N3 particle distribution basically will be proportional to the energy B into E3, energy of that particular state, plus the summation over all the energies e to the power beta EI, all the energies. Okay. So this thing is called the partition function. Okay. This thing is known as the partition function of the system. This is fixed. This is fixed for a particular problem. This partition function, the particular temperature in a system will be fixed. Okay, so this is called the partition function. For a system in which number of the particles, energy and volume is conserved, constant. That means not changing basically. This is basically the expression of the partition function. Okay. Now, so now. So Ni by N is basically is denoted as the population of a state. This is can be written as, you can write it in terms of the partition function beta equal by Q. Okay, so this is the expression of the population. P is the population in ith state. Okay. Right. So so this is it. Q is called this is the Q partition function Q. Q is the partition function. Okay. So this is it. So now the next thing is, now let's consider. So now here we have considered that this energies all not degenerate. Okay, so like this energy is not further split into two other different energies. It's not like that. The energy is all non-degenerate energy. Okay, so now if you consider degeneracy into the system, like if the energy states are degenerate, okay, this can be, this degeneracy is like can be also happens. Okay, like let's suppose uh, energy degenerate state. Okay, degenerate energy development. So let's suppose that energy level, particular energy level, that is further divided into, let's suppose E1 is given G1, G2, G3 state. That means it's 3, its degeneracy is 3 basically. Degeneracy is 3. Okay. So how can, so if an energy state is degenerate, then that information has to be there in your expression of the partition function. Okay. So in that way, if you consider the degenerate energy level into your system, your modified partition function expression would be Q equal to summation over j into Gj plus e to the power beta Eg. Okay, where Gj is basically is degeneracy of jet energy level. Okay. Okay, so let me discuss a problem here. Then. Not a problem, just some basic like properties of this partition function. Okay. Okay. So let's suppose there are this energy state. This let's suppose energy having 0. This suppose energy having epsilon 1. This suppose energy having epsilon 2. So like this, the energy states. Okay. And each state has some degeneracy level. Like this ground state equal to 0 state, let's have energy degeneracy G0. Energy 1 state, let's have degeneracy G1. Energy 2 states, let's have degeneracy G2. Like this onwards. Okay. So for this kind of system, you can calculate the partition function, right? So partition function Q would be in this case summation over J Gj e to the power beta Ej, that we know, right? So now for this case, it would partition function would be G0 plus G1 e to the power beta E1 plus G2 e to the power beta E2 plus dot 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 dot. Now, now beta you already know. Beta is related to the temperature, that is 1 by kBT. Okay. Now we will like want to focus what is the property of the system in the extremum case of a temperature. Okay, so like we take temperature tends to 0, we take temperature tends to infinite. Like what is the property of this kind of system, right? Like 0 when the temperature goes to 0 and when the temperature goes to infinite. Like how this particles are basically distributed at these two extremum cases. So what we have find out that when t tends to 0, okay, when t tends to 0, this 1 by kBt, okay, this tends to infinite, right? So that means e to the power beta e, that is e to the power infinite into t, that tends to 0, right? So that means in t to the power 0 case, the partition function will be g0 plus g1 into 0 plus g2 into 0. Like all these exponential terms basically all this exponential term into this partition function at t tends to 0 limit tends to 0 actually. So that means the partition function would be simply equal to the degeneracy of the ground states. Okay, at t tends to 0. Now what will happen if t tends to infinite? T tends to infinite. What the system will face? Okay. So at t tends to infinite, what happens? Opposite case. Okay. So at t tends to infinite, this e to the power e by kBt. This t tends to infinite means e to the power beta e k into infinite. So that means e to the power minus 1 by infinite means uh, that is basically okay. So e to the power 0, like 1 by infinite tends to 0. So so that gives you basically 1. Okay, that means you will be become to g0 plus G1 into 1 plus G2 into 1 plus G3 into 1, like that. Okay. Q would be G0, G1, G2. This would be a very like kind of a diverging type of a. This will simply not converge, right? So this will like every degeneracy would be adding up. So so this partition function would become a like a kind of a diverging number. Okay, so that means that when t tends to 0, t tends to 0, q would be tends to g0. When t tends to infinite, g like kind of approaching towards infinite. Okay, these are the two features of partition function. Sorry, this is q. Not g. This is q. So these are the like the property of partition function in like two different like two extreme case of temperature. Okay. So now uh, let's discuss a problem. Okay. So okay. So um, this is one problem. Let me first just this system consists of three independent particles localized in space. Okay, each particle have two states of energy, either zero, energy can be either zero or energy can be either E, when the system is in thermal equilibrium with a. So all of all of this statistics of thermodynamics, whatever we are calculating properties, everything is actually happening in everything is only true when the system is in thermodynamic equilibrium. Okay, so that is a very important thing you have to consider when you want to calculate any of the thermodynamic quantity that we are discussing right now. Okay, the system should be kept to remain in a thermodynamic equilibrium. Okay, heat but at temperature T. Calculate its partition function. Okay, so how could you do that? So Okay, so it's better to the way we have done previously, right? Um, it's better to do it like by using a chart. Okay, similar way like we write the configurations, the energy state, the total energy, and the degeneracy. Okay, because degeneracy is also important when you calculate this partition function and all of it. So so let's do it. Okay, so let's do it like this. Mm, there is two state basically. Either it can be so let's consider the state 1, state number possible possible on possible configurations. Total energy and degeneracy. Total energy and degeneracy. Right. So state 1, in state 1 we will consider like there are only two energy levels, right? Either it can be 0 or it can be E. Okay, so similar way let's name this particle as these are like all particles are distinguishable, independent particles. That means the particles are distinguishable. Like indirectly in the problem they want to specify the particles are distinguishable. So let's name this particle as A, B, C. Okay, three particles are there. So let's consider the case 1 where all particles are downstate. State. So there, so that means all ABC is having this zero energy. So that means the total energy of the system will be 0. Now the degeneracy, like the for this case would be 1, because the number of configuration you can see this is the only single configuration to get this state, right? Like all the particles you have to put into the ground state, right? This is the only configuration that can be possible. So the degeneration will be 1. Now let's consider the second case where let's take two particles in E and one two particle, let's suppose in 0, first ground, two particles in ground and two particles in E state. So for that the combination will be, so it can be if this is 0, so it can be A, B, C is there, or it can be B, C, A is there, 0 and E, 0 and E, or it can be C, A and B is there. B is in the E state. Okay, so these three are the combinations. Okay, so in this case anyway, any three, for all these three cases the total energy would be E and the degeneration will be 3, right? Because the configurations you can see is 3 here, 1, 2, 3. So 3 configurations is there. Degeneracy will be 3 for this case. Now for this energy, okay. So now this is 1, this is 2. Now the 3 for 3, third one. Third one would be, let's consider one particle in ground and two particles in the energy state E. Now for this case, what are the possible, like the opposite of the second one, right? So this case, for this case, let me also write the possible configuration. So that will be So A, B, C, or it can be B, C, A, or it can be C, A, B. Right. So this is also three combination. Now in this case, what would be the total energy? 2E, right? Two particles are in the energy state E and one is in 0. So that means, so the total energy for this kind of configuration would be 2, right? So total energy would be 2E. And for this case, the number of microstates will be also 3. It's also 3, right? Okay. Now the last one is like all of them is in the E state. 3 are in the state E. So for this case, the only configuration is can be possible is like this. So this is E. So all the three particles are in the E state. This is the only single configuration that is possible. So in that case, it says so the particle energy is total is 3E and number configuration is 1, right? So you get it, right? So these are the four possible states and these are all the possible configurations and total energy and the degeneracy all I have mentioned. Now having all of that, you can write a partition function, right? Because you know the energy under each energy states. That's and also you know the temperature is specified in the problem, right? It's in a thermal equilibrium with a bath of having temperature T, right? So for this system, the total what do you call the total uh, uh, this partition function is summation over I gi e to the power minus beta ei. Okay. So this is the partition function. Sorry, this is gi. So now you can calculate it. You can simply it's not g1 into e to the power beta e1 plus g2 into e to the power beta e2. There are four states is there. So e1, e2, e3. g3 into e to the power beta e3 plus g4 into e to the power beta e4. So here q is g1 is here 1, right? This is g1, this is g2, this is g3, and this is g4. Similarly, this is e4, this is e3, this is e2, this is e1. Okay. So g1 is what is g1 is 1 into e to the power beta 0 plus 3 into e to the power beta e plus 3 into e to the power 2 beta e plus e to the power minus beta e. This gives you q equal to 1 plus 3 e to the power beta e plus 3 into e to the power minus 2 beta e plus e to the power minus beta e. So this is the whole expression of the partition function. Okay. So it's actually dependent on the both energy and temperature. Okay. So so this is a way, but for this way, this is like we can like this problem is like only for three particles. So because of that, we can write it in a very simple way. We can like write this each energy state and how the possible ways the particles can distribute in the each energy state. This is only we like this whole table we have derived, like we have done it because the problem is a very like problem. This problem is basically dealing with a very small number of particles. That is the reason you can able to do it. Otherwise, if let's suppose this number of particles become higher, like 10 particles, 20 particles. Forget about 1000 or particles in lakhs or something like that. If it's 10, 20, like, then it is impossible for us to do it in this way, right? So for that, there is a like a formula which you can use to calculate the partition function. Okay, that formula is this. Let me write it over. So for n particle system, uh, uh, in in this case, the particles are distinguishable particles, right? So for n distinguishable particles, Qn, the partition function would be simply Q1 into to the power 1. So here Qn is basically the partition function of n particle system, and 1 is partition, Q1 is partition function for one particle system. So which means that for this problem, in this problem, Q1 means if there is only, instead of three particle, if there is one particle, then the configuration was like, if there is two energy level, E or 0. So either the configuration is, either the particle is on 0 state or the particle can be in E state. So in that case Q1 would be simply, there is nothing degeneracy will be there. So E1 would be e to the power beta into 0 plus e to the power minus beta into E, right? Either the particle is 0 state, so to the power beta 0, or the particle can be in E state, so e to the power minus beta E. So Q1 would be 1 plus e to the power minus beta E. So this is the single particle partition function Q1. Now from Q1 you can calculate Q3. Q3 is the three particle partition function, that is simply Q1 to the power n. So 1 plus e to the power beta E to the power q, that basically gives you 1 plus e to the power minus 3 beta E plus 3 into e to the power beta E, sorry, 2 beta E plus 3 into e to the power minus beta E. That is the same thing that we got here, right? Like this is the same thing that we are getting here by using this symbol. So this is basically a very useful technique that you can use to calculate the partition function when the number of particles become very much higher. Okay, so this is it. So I want to now conclude the session. If you have some question, you can ask. Otherwise, I can just stop the meeting. Okay. Okay, then that's it. Okay, so I am now stopping the meeting.